So good morning to this second to last lecture in time series analysis. So I'd like to start just presenting a screenshot from my cell phone that I made a while ago now, because this is what it's all about. Unfortunately, my smartphone is now working again. I was out running, and then I looked at where I had been afterwards, and I saw this. I don't know, how many of you have seen anything like that whenever you've been using kind of a GPS tracker of any kind? Or is it always just like nice and smooth? It's typically nice and smooth, right? So last year, I didn't take this particular data set because unfortunately I lost it, because it could be fun to use. But last year what I did for one of the assignments was to actually go out and use my phone just to log some points and then to try to trace that as a bivariate process. Now, then I tried to fit a Kalman filter to it, and it said, what is the system noise? 0. It's like, how come? Why does that happen? And I thought I had an app that could get the sensor, the raw logging, not any filtered stuff like that. But even on the chip, it's filtered with a Kalman filter. So what I get out is the filtered data. I cannot get the raw measurement of the position. Using a device like this, then you need to have something different. So at the end of the day, it wasn't that fun to do, but it's happening all the time. Just to kind of add a comment to, and I think that run there became like at least 50% longer than what I thought it was, as in kind of the usual run. But imagine if I had done that. But that's reality. When you sample every second and you move at a certain rate and your position is like 10 meters, you will get measurements like that. I could, of course, just put some white noise stuff on top of it, and then you could still filter this. How would you model stuff like this? If you were to make a Kalman filter and you had like this, how would you model this? What would be your states? So your observations will be, you can say, latitude, longitude. But how would you model it? What should be your system? Yes? So you would want to have a velocity. Yes. So one way of phrasing it, if you just look in one dimension, then you will want to have the location in that direction, and then you have the velocity in that direction. That could be your this could be your state, and then you do the same in the y direction. That could be one state vector. Sorry, yes. Thank you. I could just see your face. There's something I did wrong. So that would be one representation of that system. Is it good? It's good for most of the time for that kind of data, but it will fail on one particular point. Yes? Exactly. So what happens when I turn? With this assumption here. I can tell you, I came from here, and then I made a right-hand turn. What happens to my velocity when I turn while I'm running? What do you expect that I do? Do I keep running, or do I stop and then I keep running again? I probably run around the corner, right? So having an estimate here where, as you said, it's the velocity in the x direction is probably constant. But all of a sudden it's 0 because I turned. So what's the challenge here? It gets back to what you said this morning about modeling. How do you represent a system? I fully agree, you need to know something about the velocity. But what would be the obvious thing to do when you track someone? You look at the velocity and one more thing. It's kind of obvious, I think. Yes? You can do that, but I don't think that's needed here. Direction, yes. So you keep moving in some direction, then you can say the velocity is unchanged, but the direction changes. Then there's only one of the states that is wrong, that you need to update. So you can have a smaller variance on the velocity, as you indicated in the beginning, but then you can have a larger uncertainty on the orientation or the direction. So then you can actually, rather than having 4 states, you can go with 2 states. Then you have a problem, because then the mapping from direction in, say, degrees to observations, is that a linear function? No, not anymore. So you won't be able to do this. You can do this representation in a linear Kalman filter setting, but to do the other, you need to do an extended Kalman filter. That's a different course, advanced time series analysis. But just to make you think of many different representations of things. So today, we will just quickly revisit ARMA models. We will look at a random walk in a couple of different settings, and then get back to the Kalman filter, say what if observations are missing. I was out at what is now Ørsted, former Dong, yesterday, and talking about how to do things. And when I had this comment about missing data, and they said, well, always. I mean, there's never a complete series. There's always gaps somewhere. Pretty much. I mean, even if you sample things yourself, it will be missing sometime because of whatever, power failure. There's always gaps somewhere. Things can be time varying. And then another example. So first, just state space models. We looked at this last week, so I won't say much about it. I just want you to mentally just remember the system equation and the observation equation. And the ARMA model, I don't know if you recall, but we said that any ARMA process could be written as a vector autoregressive model of order 1. And I remember one of you asked, is that a state space model? And I answered yes, even though at the time we had not mentioned it here, because it's basically just the same thing that is written here. It's just representing it as a state space model. What is different to, you can say, the usual state space models, I don't know if you can see what that is. There are 2 things that are different. One is easy to see, and the other thing is not so easy to see. Yes? Yes, so there's no observation noise. So you assume that you observe the state directly. And that's also one of those things that I like about the Kalman filter, is that all of a sudden you take a model and you say, well, actually you accept that there is a measurement observation error. It's not just system noise. And the way that you can split that noise between how well is your description of the system and what is just a measurement error. I like that, but there's one more thing, and it's not so easy to see. I can say it has to do with the system noise. Consider everything here. All parameter values are scalars. And if you have a d-dimensional system, what is your typical dimension of your noise? So what is the dimension of this G there? You have one column and D rows in that matrix. So what is the dimension of epsilon? It's a univariate white noise process. So where you would normally have a d-dimensional noise signal that goes in this case you only use a one-dimensional, a univariate white noise signal. Because in an ARMA model you only have one random error coming in. So basically what you're saying is that if you were in the traditional setting, then you would have a 1 theta 1 down to theta d minus 1, and then you would pad with a lot of zeros out there. If you had an implementation of the Kalman filter, you want to use this, and it's not flexible with regards to what is the dimension of your noise, then you need to have this structure here. Now, if you take this state space model here, it's just a random walk in the state here, and then you just make an observation with noise of that. So you have a random walk that you observe with noise. And both eta and epsilon are considered to be white noise, and they are, as the usual, IID distribution with each their own variance. And what is actually y? What is the process for y here? If you look at just observing y and you think of how can we represent this? Can we think of an ARIMA structure that actually gives us the same as this? This is where you just spent 5 minutes with a piece of paper. And saying, well, how do I get about that? I can give a hint. You want to make diff on y. You want to look at diff of y. Sorry? Maybe, I don't recall. So you remember what it is, the answer? So then if you don't remember the answer from the book, then you just work it out now. If you have seen it and understood it, you can easily redo it. Even harder. But it's just to see what happens when you add extra noise. So the hint was to look at the difference of y. Anyone? How close are you to something? There's one thing that is not so obvious in this calculation. So diff y, what does that give us? Yes? Eta? Yeah, so just to make everyone follow you, I mean, you're correct. Just take it one step at a time. So you have nabla on x of t plus nabla on epsilon t, if you just plug in, and this one here, that is just equal to, if you look at the first top equation for the system, and you subtract x t minus 1 on both sides, then you can see that this here is exactly eta t, as you say. So what I get here is eta t plus, and then this. Exactly. So that was not so hard. What is, I think, harder is to say, what is this actually? Well, it's not just white noise, because there's epsilon t and epsilon t minus 1 in here. And then you add some more white noise. So when you look at a white noise process, then you don't have a dependence on the previous one. So when you have a dependence on the previous noise, what would that be? Which kind of model would that be? So that's an MA1 model. But now what happens to this one here? That was not taken into account as such. But we can define a new random variable that kind of corresponds to this, and then you have kind of this out here as well. So we can consider it that it's similar to an MA1 model for diff of y. So actually it's an ARIMA 0,1,1 or IMA 1,1 model. That gives you, you can say, similar performance. It will not give you the exact same epsilons, but it will give you similar performance. So that's what is written there. And if you keep looking at it, just to look at what is the autocorrelation function for it, that's also how to identify, I mean, one way of identifying what it is. Then you will see, of course, for lag 1, lag 0, it's 1, and in lag 1, you have a dependency because of epsilon t and epsilon t minus 1. And then whenever you get to a lag that is greater than 1, all the epsilons and etas, they have different time stamp, so you get a 0. So that's why you can say it's an IMA. And then you can solve, I think that's on the next slide, what is the parameter here? Well, you get that from that coefficient there. If it was a traditional MA1 model, then you have that relation. So basically, you have two sets of equations to say what is actually the parameter theta here, and what is the variance of my new epsilon with this not on here. So that means basically here, this ARMA process, sorry. So the MA part here, the parameter there comes from a relationship between the variance of the state and the variance of the system, observation. So it's just a different representation. It's just to say that things are connected. And many of these models, you can find, you can say cases where you can get from one class of models to the other. But you can also say that, you can say the state space model is much richer than just being able to represent other function models in weird ways. But the important thing is that if you go back to the ARMA model here, all of a sudden, when you start including observation noise up here, it's not just an ARMA model. Even though you have an ARMA structure in the A matrix, you actually get something more. I think that's important to just remember. And that's the purpose of this step here. Now, once again, flashing that slide, have the state space model with the state equation and the system equation. We looked at the Kalman filter last time, and what happens if an observation is missing? Because I said earlier on, that always happens, right? Unless you sample or simulate the data yourself and know the model, then quite often you will have missing data. What I try to do when I give you assignments is to either fill in gaps or to trim the time series so that you get it without gaps. But there are always, not always. Of course, there are things that you can get everywhere, every time. But in real-time applications, you need to be prepared that things are missing. So what do you do? First of all, the initialization up there, is that going to change if you lack observations? No. How about the prediction here? That was the order we did things in last week. If you do the prediction, does that depend on the next observation? No. The only thing that depends on the next observation is that if you don't have an observation, you cannot do this. Because then you don't have something here, you don't have anything to update your estimate with. I don't know if you recall the drawing I made last week. That's where I need color chalk. Today will be just white. That when we had time, and then we had, at a given point in time, we had a distribution for our one-step prediction, and then we got an observation at some point, and then we made a weighted average of those two normal distributions, and then we got a posterior. At least one more color here. Estimate of where we actually are. And then we took this estimate here and predicted that forward in time to time t plus 1. And then we get a prediction around that. Now, if we don't get an observation, what happens then? What is the best thing we can do as for the reconstruction here? What is appropriate? We don't have that observation, so we cannot calculate the one-step prediction error. So what would be the appropriate thing to do? It's kind of obvious, I think. There's only one thing that is, I think, at least in my mind, that is meaningful, and I'm sure you can guess it. What makes sense? If you don't have an observation, how much information do you gain? Anyone who's good at reading lips? Yes? You don't gain anything. So what do you do? If you don't gain any information, can you then make a reduction in variance as you did here? No. So what do you do? You cannot calculate the update here So you basically just have to say that my reconstructed xt given t, given information up to time t, is the same as what I predicted, because I did not gain any information. Likewise, well, you do have these numbers for the common gain, but since you did not gain any information, you should not use that to reduce your variance. So basically, what it means is that your posterior is the same as your prior. And then you take this one here, and then you predict to t plus 2. And that means that now the variance is even greater than what it was there. So now you get something, and I'll just over-exaggerate a little bit, that is very, very uncertain, where the mean value should be there, so it should peak there. Something like this. And then hopefully you get an observation then, because all of a sudden, otherwise you're just losing everything. Yes?
Where did you know observations on both sides? You get time to
I'll show you. I'll show you how it works. Yeah, then it's no problem. If you use a Kalman filter. But if you use the ARIMA model, it won't work. Because when you look at the ARIMA structure, I think I have it here at the top. If an observation is missing, that means the next P element here, you cannot make predictions. And basically that means that you start from scratch again, because you cannot predict something if something is missing. So if you have one observation missing up here, then you cannot predict. But then after the fact, you cannot solve the epsilon either. So you're just doomed. Pretty much. It's basically, whenever you have one observation missing in the middle, you have to treat it as two separate time series, because you just have to start over again. Pretty much. Unless you do some stuff. And that's what the Kalman filter, basically what it does is that, well, it just adds some more uncertainty to that, so it doesn't give you much weight. For the likelihood, it doesn't contribute. We'll get back to that. And then you just keep going. And everything works fine. So that's a robust way of doing it. So this is basically saying how to do things. We just did it in words just before. Of course, you can also estimate parameters in this way, because we can do maximum likelihood in a state space and a Kalman filter representation as well, and use that to estimate parameters. So, returning back, how many parameters do we have? Well, that depends on the order. Here I've written, you can say all the possible coefficients up to the order d. So that's 2 times d minus 1, because we fixed that one up there. But in practice, you can say you may not need to use all these parameters. So that's the system that you want to estimate. If you're going to do maximum likelihood estimation in the generic state space model, here I added some observation noise again. I always like having that, because it makes everything more generic. Then, well, how many you have parameters in the matrices here, and you also have the covariance matrices that you want to estimate. But the general setting is that you formulate what the structure should be. Say, if you had this structure here, what would be your prediction? What would be your state estimate? That would actually not be something you want to estimate, because that's fixed. Maybe we should work it out. If we look at this at time t, location x, velocity x, location y, and velocity y, t minus 1 plus some noise. How do we get to the location at the next point in time? I'll just state it. It's the location at the previous point in time in the x direction plus the velocity in the x direction. It does not depend on your location or velocity in the y direction. The velocity in the x direction does not depend on where you are. You get a 0 there. You expect it to be the same as it was before. And then, of course, we have some white noise stuff out there, so it's a random walk in that. And the velocity in the x direction is initially not assumed to be influenced by what happens in the y direction. And the y direction is just the same as the x direction. So we have a 1, 1, 1, and the rest are zeros. So if you have a system like this, basically, you don't want to estimate these parameters because you cannot speculate that as part of your assumption for the model. What you don't know are what are the uncertainties out here. So you have a diagonal matrix for, or at least diagonal elements for the covariance structure that you want to estimate. And maybe some observation noise as well. So the likelihood here goes as we've done it many times before. We want to look at the likelihood of a particular set of parameters given all the observations that we have observed. And that's the joint density, n-dimensional density, joint density probability function of observing those observations given these parameters. And as we discussed, we don't like large multivariate things if we can do it as a lot of independent univariate things. So we will do the same thing to say that this density here, when we look at the Kalman filter, like we did for the ARMA model, we can look at the y-nth observation given the distribution of that, given all the previous ones. Since it's a Markov process, we have one distribution there multiplied by the density of all the previous ones. So this is a, well, depending on the dimension of y, it may also be multivariate, but it's much smaller dimension. And we can repeat that argument because yn minus 1, that observation is independent of, I mean, when you condition on information up to yn minus 2, it's independent. So you can make a product of all the independent one-step prediction errors. What is the distribution for those? And it runs fine. And you can find all these conditional densities by using the Kalman filter, because we're looking at the expected one-step prediction error for the state and the covariance for the state, but that's not what you should use. What you should use is for the observation. So that's the expected observation, because that's what you compare with the actual observation. And then you have the covariance matrix for the one-step prediction error as well. So those are the two, the mean and the covariance matrix that you want to compare with your actual measurement at time t+1. So everything here are just normal distributions. So we are back to the usual suspects. Oh, comes a little bit further down. So what you have, didn't I have that slide here? Oh, it comes in a moment. So this is the usual part you run here, and basically when you get to the likelihood, we just have to look at all those one-step prediction errors and their distribution, and what is the likelihood of observing a particular observation given that prediction, and then just make a product of all those. But stepping back to what happens if something is missing, we discussed it before. If we have the YT observation, then we can do the usual reconstruction. If we don't, then we just say that the one step, the reconstruction is just the prediction that we made before, And the one-step variance here, or the updated variance, is also just the variance that we had before, just as we just discussed down here. So we have the prediction errors up here, the observation minus the prediction, and we have the covariance matrix for this. And assuming normality, we just have this, the usual product of all the independent normal distributions. Yes?
Like I missed an observation and like, let's say times 50, and I really want to know what it was. Like, do I only use the time steps before to try and predict it? I don't also use the one after to try and reconstruct what it was after. Like, I'm really interested in what it was.
If you really want to know what happened at a particular point in time where we lost it, then you'd call it smoothing to get an estimate of that. But in order to estimate the parameters, you do not have any information there. We discussed that just before. So you cannot use it for estimating the parameters in the model, but given the model when you've estimated, then you can, as you kind of indicate, run the filter both forward and backward and say what is the most likely value that you actually have there. Not just using the past observation up to the point in time, but also using the future. So in practice, you can get the answer that you want, but you first need to estimate the parameters. And the missing observation should not be part of estimating your parameters. You should leave that lack of information out. That is also why everywhere here it says n star, so that is only including those that you actually observed. So if you only observe 5 out of 40, you have 5 pieces of information. Tough, but you'll get by, hopefully. So that's how things are. And in practice, as I said many times, you do not look at the likelihood, but you look at the log likelihood, because numerically it's much more well behaved. And then the variance of these estimates, if you do the second order derivative of the log likelihood, then you can find that variance in a similar way to what we did previously for the AMA model or any other model that we looked at. That's one way, or you can also do what is called profile likelihood, which in particular for some of the parameters where, say, if you have an AMA model, you want it to be stationary. So you will see things that is not symmetric depending on how you define your parameters. I'll show you an example in a moment. Depending on how you define the parameters you optimize, then you may end up having something that is not meaningful. And that's not nice, but that is just something you have to think of, so be careful out there. When you want to initialize this, we kind of looked at this last week, but I will just say it now, and then I will show the example from last week again. You need to pick an initial value for the filter, and you need to pick an initial covariance matrix. Sometimes you just say, I start at 0, and you start with some independent uncertainty on where I'm at. That may work. You can also say that you start somewhere where you fix the initial state as something meaningful, because 0 is probably not always meaningful at least, and then you say that I know exactly where you're at. I do recommend that you do a combination of the two. You want to start something somewhere meaningful, and then with an uncertainty that matches what is the actual uncertainty. I mean, if you know where you're at, it's fine. But assuming that you know exactly where you are, and you have a very noisy measurement, and you have a noisy process, I mean, in practice, it's not going to happen, right? So you should pick something that is meaningful, and as I'll show you in a moment, it's better to pick an initial covariance for the state that is slightly too large than slightly too small. That's but let's just go and revisit the falling body. I think I did that. So I'll first just do the simulation that I did last week. And here I have over time what is the elevation, and then the black line is the state, and the red dots, circles there, those are the observations that we have. And the velocity just goes more and more negative. I think I did. So that's my Kalman filter. If you don't want to implement your own, I can say, look at library FKF. So it's called fast Kalman filter. It has almost the same structure. The only thing is that A, B, U, C, and so forth, all those, you can say variables in there, they have different names, but it actually does the same thing. And the implementation is much faster than what I have here. And it gives you the likelihood out as part of the result, which I did not build into my function yet. Because I want you to see how you actually calculate it, not just have it under the hood. This is just a description of what goes in there. So redoing what I did last week was to start knowing exactly, starting at the right position and height, and assuming, where is that? That my initial covariance matrix V0 is just 0, so I know exactly where I'm at. And then I will redo this plot. And what I'm plotting is now my one-step predictions along with the prediction interval for that. And when you look at it, I mean, you're almost crying, right? But we also know that we were cheating because we used the exact same parameters that we use for simulating and the exact correct observations and stuff. So that's cheating. But it's nice that, I mean, if you cheat, that you can actually get a nice result. I mean, we should not neglect that. So in practice, let me just say that you just start somewhere. And in this case, I started 6,000 meters above ground. I again assume that I know exactly where I'm at. So it's not likely to happen in practice. And then this is what you will get. It will have a hard time to start to fly upwards because you said you knew exactly where we were. So the uncertainty on the state would be very, very small, and the observations are noisy. So even though the standard error on the observation is only, in quotes, only 100 meters, and you're 4,000 meters away, it will only slowly start to go up. And then we'll overshoot. If I instead say that the initial estimate of my location is not 0, but 100,000 as variance, still starting at 6,000 meters, and then just adding that on top. So that's the influence of starting in the wrong position with the wrong estimate of the covariance versus starting in the wrong position with a good, I mean, with a reasonable or representative estimate of the initial uncertainty. I still assumed that the velocity was 0. So here you see that within, I think it's 3 samples, you're actually very, very close to starting at the perfect spot. So that's when I think things are nice. And I think that's a very good example as to say it's better to start with a little too much uncertainty. In this case, it's also a little bit, you can say, let me just check one thing. I didn't do that. It's a little bit, you can say, optimistic in the sense that you say that the observation error is much greater than the system noise. Sometimes it will be the other way around, and then you have to be more careful. But what I wanted to get to is the fact that you have missing observations. So I'll just make a copy of all the previous observations, and then I will take 30. So how long is y? So I had 47 observations. Now I will take 32 of those and write it at random and make them NAs. So now this is my observations that I have left. Let me just plot it so you can see this is what we have. Now the question is, will this work? Let's just run the filter through. Now again, I will start at the optimal true initialization. I know it's idealistic, but let's just try it. Did you expect that? Yeah, you're just nodding because, yeah, you can see I'm smiling. That's fine. So why is it that good? Can you figure that out? I mean, you have long gaps with no observations. Yes?
You don't have that much system noise.
Exactly. So it means that the inflation from one time point to another is almost nothing. Relative to the measurement error, it's nothing. So it works very, very well. So what I will try now is that I will not use a different data set. I'll use the same data set, but I will say that my system noise is 100 times greater in variance. And just add that. I mean, you can see the green stuff outside, but it's not. Maybe I should actually make them thicker. Yes?
Have you actually added the noise to the measurement? Because like your data doesn't have, your data is still not noisy. You just like telling
I'm just telling the filter that my system is more noisy. I did not simulate with more noise. We can try doing that, but then you will see something weird stuff. Then you don't want to fly in that plane that drops like this. I've tried simulate with a lot of noise, but we can. Let's just go and do that. Let's simulate. Let's say that the simulation here, the system noise, is 100 times greater, and then just rerun the simulation here. So now we have similar thing. Let's just plot. It still looks like something that could be just normal falling down. I tried actually going up to multiplying by 100 more, and then you start seeing a drop that doesn't look like a drop anymore. So let's just go down and get to the point where things are. Maybe we just run it first. No, let's just now we need to resample. We copy. Oops. And then we remove a lot of observations, so now we have this. This is what you have. This was with the optimal. Now if I increase, again here in my filter, to be, first I did it with the simulation, it's 100 times greater, but now in the filter I will again do it 100 times greater than that. Now you start to see things happening, right? And if it's even greater, so now I'm going to make it 1,000,000 times the original thing. This is probably going to be too much now. That's where you start to break down. Now, how many observations do you actually need? I had 49 observations here that are above ground. So let's say, what if I only had, how many should I leave? Let me put 39. So I only have 10 observations left. What? Because I did not make it a fresh start. That'll do. Still behaves quite nice. if we go down to the large uncertainty down here, this is a seasonal thing. Do you see the same thing as I see? It's a strong eastern wind. Yes?
Pretty small uncertainty when you have a lot of observations.
Yeah, exactly. So when you have... Yes, so when you have, you can say, consecutive observations that are close, then you have a small variance, and when you have a large gap, then you see a larger uncertainty. But it just grows and grows and grows. So, but now we have an uncertainty on the state of the order of 20 meters. From 1 second to the following second, you're allowed to jump. You have a standard error for the jump of 20 meters. So that's what I'm saying is I don't want to fly that airplane because that's where turbulence gets messy. I tend to say this is a kind of a Christmas tree in a strong wind. So the likelihood calculation. Now I change things upwards. So what you have to look at for the likelihood. Here I have the prediction errors, have my observations. I have to leave the first one out because I need to predict the second one. And then I have my predictions, and the function gives me one too many, so I have to kind of keep track of which numbers to keep in and which to leave out. So I remove the first and the one that is too many. And then I normalize that. I have those squared, and then I normalize it with the prediction variances. This was what that's because I did not run everything after redoing things. The problem is that I just need to run the filters up here with the wrong start and the right start. My y vector, since it's at random when it hits the ground, sometimes it's 49, sometimes it's 47, sometimes it's 46. So when I reran the filter again here, all of a sudden I got a different observation vector. So of course then it doesn't provide what I want it to be. So now it should be fine. So this is for the likelihood for the first where I start with the correct values and with optimal settings. This is when I start at minus 6,000 meters, so I'm totally off, but I assume I know exactly where I'm at. You can see the likelihood is much less than this. And this is where I again start at 6,000 meters, but with a large uncertainty. So what you can see here is that you can say this is of course the best one, where I'm starting at the true values, but if I just start at a wrong place with sufficient amount of uncertainty, the likelihood is not that much smaller compared to starting at a wrong place, assuming that you know that where you are. And I think that's the important part of it. Now the next part, I think we should have a break now before going into that, because I wanted to follow that part. So let's resume 5 minutes past 9.